Hello friends, so welcome to a lecture series on multivariable calculus. So in the last lecture we have seen what do you mean by partial derivative of multivariable functions. Okay. So now we will see second or higher order partial derivatives. So what do you mean by this? Let us see. So again suppose z equal to fxy, where x and y are independent variables and z is a dependent variable. Now we have already seen what do you mean by fx at a point say a comma b. It is simply del f upon del x, which is limit s tending to 0 f of a plus h comma b minus f a b upon h. And similarly fy at a comma b is equals to limit s tending to 0 f of a comma b plus h minus f a b upon h. Now suppose we define del square f upon del x square. Similarly, we define second order derivative for single variable functions f double dash x. Okay. Here we define second order partial derivative of f with respect to x. It is also denoted by f x x. So at a point, suppose we are defining it at a point a comma b, at a point a comma b, it is simply limit s tend to 0 f x of a plus h comma b minus f x of a comma b upon h. Because what does it mean basically? It means del f x upon del x at a comma b. It means del by del x of f x. That means now you have to take f x as a new function and you have to apply the definition of del upon del x in f x. So we have applied definition of del by del x in f x as f x a plus h minus b, f x of a comma b minus upon h. We simply replace f by f x in this definition, so that we can get del square f upon del x square. Now similarly, if we define del square f upon del y square, that is second order partial derivative of f with respect to y at say a comma b, which is can be defined as del by del y of del f upon del y at a comma b, or also denoted by f y y at a comma b, is simply given by limit s tending to 0 f of f y of, because now you have to apply the definition of del upon del y on f y. Okay. And del upon and f definition of f y is this. So you have to simply replace f by f y here. So that means f y of a comma b plus h minus f y of a comma b upon h. So this is how we can define second order partial derivative of f with respect to x or with respect to y. Okay. Now come to mixed order partial derivatives. Mixed second order partial derivative of f with respect to x or y. Now suppose we want to define del square f upon del x del y at say a comma b. It is del by del x of del f upon del y at a comma b, or we can say it is f del of f y of del f upon del x at a comma b. Okay. So this is by definition we have to replace f by f y here in this definition, because it is del f upon del x, and instead of f we are now having f y. So that will be limit s tending to 0 f y of a plus h comma b minus f y of a comma b upon h. Okay. Now, this mixed order second order mixed partial derivative can also be represented as f of y x, because it is what? It is f y with respect to x. That means del upon del x of f y. That means I differentiate partially this function with respect to x, that is del upon del x of f y, which is same which is here. So, we can also represent this this partial derivative as f y x. Okay. Now, the second one is del square f upon del y del x, which is at a comma b, which is also represented as del by del y of del f upon del x at say a comma b, or it is f of x y at a comma b. Okay. It is by the definition we can write it like this, it is limit h tending to 0. Now, you have to apply the definition of del upon del y on f x. So, it is f x at a comma b plus h minus f x at a comma b upon h. So, this is how we can define f x y or f y x. So, f x y or f y x are also called mixed second order partial derivative. Now, let us try some problems based on this. So, these are all second order partial derivatives with respect to x or y. Now, suppose f is 2x minus 3y whole cube. Now, what is f x? It is t cube. T cube is 3t square and del by del x of t again, which is 2 here, and 2 into 3 is 6, 6 times 2x minus 3y whole square. And again, and f y is similarly, it is 3t square, t is 2x minus 3y, and it is del by del y of t again, which is minus 3 into 3 is minus 9, minus 9 2x minus 3y whole square. Now, suppose you want to compute f x x. F x is means del by del x of f x. Now, del by del x of f x is you have to differentiate f x with respect to x again partially. So, when you differentiate this partial respect to x again, so what we will obtain? This is again 6 into t square, which is 6 into 2 into 2x minus 3y raised to power 1 into del by del x of t again, which is 2, 6 into 4 is 24, 2x minus 3y. Now, if you want to compute f y y, which is del by del y of f y, and it is differentiate this function with partially respect to y. So, it is minus 18, 2x minus 3y and del by del y of t again. So, that will be 54 times 2x minus 3y. Okay. Now, suppose you want to compute f x y, which is f x of y. Okay. That means del by del y of f x. Okay. So, del by del y of f x, this is f x, the del by del y of this function, that is differentiate this partial respect to y. and that means it is 12 2x minus 3y del by del y of this again with respect to y, that is minus 3 into 12 is minus 36 times 2x minus 3y. Now, fyx, suppose fyx fy with respect to x, that is del by del x of fy. That means it is fy, you have to differentiate this partial respect to x, that means minus 18 2x minus 3y del by del y of, or del by del x of this function 2x minus 3y, which is minus 36 times 2x minus 3y. So, that is how we can compute second order partial derivatives with respect to x or y. Okay. Now, see again say second problem. So, what is second problem now? It is f equal to x upon x square plus y square, and x y should not equal to 0 0, because there is a problem in 0 0. So, we are excluding 0 0 from the domain. Okay. Now, what is fx? First we compute fx. Fx is, now x is a numerator and x is a denominator also. So, we have to apply quotient rule, that is denominator derivative of numerator minus numerator derivative of denominator, that is 2x upon denominator whole square. So, this will be equals to y square minus x square upon x square plus y square whole square. Okay. Now, what is fy? Now, it is x is constant for this partial derivative of f with respect to y. So, we take x into del by del y of 1 upon x square plus y square. So, it is x into 1 by t, that is minus 1 by t square. So, it is minus 1 upon t square, then t again, that is del by del y of t, and this is 2xy upon x square plus y square whole square and with negative sign. So, this is del f upon del y. Now, you want to compute second order partial derivatives. Again we can use this thing fxx, which is del by del x of fx. We have to differentiate this again with respect to x. Okay. So, it is denominator as it is, derivative of numerator which is minus 2x minus numerator derivative of denominator, it is 2 times x square plus y square, and it again upon denominator whole square. Okay. So, this will be minus 2x x square plus y square, and it is x square plus y square, 1 is cancel out, it is minus 2x square y square, and it is minus 4x y square minus x square upon x square plus y square whole cube. Okay. And it is equals to, it is minus 2x cube, it is plus 4x cube. So, it is 2x cube, and it is minus 2x y square, it is minus 4x, that is minus 6x y square upon x square plus y square whole cube. Okay. Similarly, we can find fyy also. Now, let us compute one more term here, it is one of the mixed derivative, any one, say we compute fxy. Fxy is fxy, that is del by del y of fx. That is simply means you have to differentiate this partial respect to y. So, again denominator as it is, derivative of numerator minus numerator derivative of denominator 2t, t again that is 2y upon denominator whole square. So, this is further equal to, you cancel x square y square from numerator and denominator. So, we will obtain 2y into x square plus y square, and it is minus 4y y square minus x square upon x square plus y square whole cube. So, this is 2y cube minus 4y cube, that is minus 2y cube, and it is 2y x square, it is minus minus plus 4y x square, that is plus 6y x square upon x square plus y square whole cube. And similarly, we can find fyx. So, that is how we can find fxx, fyy, fxy or fyx. Now, let us solve one problem of 3 variables. Now, suppose fxyz is x raised to power x, y raised to power y, z raised to power z, where x, y and z are non-negative. Now, you have to find, here you have to find fxx, all second order partial derivatives for this function. So, how will you compute fx? So, you have to take log first. So, log of f will be equals to x log x plus y log y plus z log z. Now, differentiate this equation partially with respect to x. So, log t, that is 1 upon t, and t again, that is fx. Now, here both are a function of x. So, you apply product rule, first as it is derivative of second plus second as it is derivative of first, and these two are independent of x. So, derivative will be 0, partial derivative will be 0. So, this implies fx will be f into 1 plus log x. Of course, it is base e. Okay. Okay. Now, similarly, fy will be f into 1 plus log y, and fz will be f into 1 plus log z. Now, suppose you want to compute xxx, fxxx. So, how can you compute this? It is del by del x of fx, which is, so you have to differentiate this again with respect to x. So, this is also a function of x and this is also a function of x. So, you have to apply product rule. So, f first as it is derivative of second plus second as it is derivative of first fx. And what is fx? What is fx? Fx is this. So, it is f into 1 plus log x whole square. So, this is fxx. Now, similarly, fyy will be, because it is symmetrical in x, y and z. So, we can simply write fyy as f upon y f 1 plus log y whole square, fzz as f upon z plus f plus 1 plus log z whole square. Okay. Now, suppose you want to find out f, suppose x fxz, that is fx at z, that is del by del z of fx. Now, what is fx? Fx is this, and you have to differentiate this fx with respect to z partially. Now, this is independent of z, because x, y, z are independent of each other, independent variables. Okay. So, it is 1 plus log x you can take outside, and this is a function of x, y, z. So, partial derivative of respect to z will be f z, and f z is f 1 plus log z. So, it is f 1 plus log z log x into 1 plus log z. So, again using the symmetry we can simply say that f y z will be f into 1 plus log y into 1 plus log z, and similarly f x y will be f 1 plus log x into 1 plus log y. Okay. So, that is how we can find out all mixed second order partial derivative for this function. Now, the next problem, prove that the function this satisfy this equation. So, again this is a simple problem. Let us see how can we show this. What is f here? F is e raised to power 3x plus 4y and cos 5z. Okay. Now, what is f x? Now, it is e raised to power t. So, e raised to power t is e raised to power t derivative, cos 5z remain as it is, and t again, that is del by del x of t again, that is 3x plus 4y, which is 3 times e raised to power 3x plus 4y into cos 5z. Okay. Now, what is f x x? The derivative of this again, partial derivative of this again respect to x. So, that will be 9 e raised to power 3x plus 4y cos 5z. This is 1. Now, compute f y. F y is 4 e raised to power 3x plus 4y into cos 5z. We can directly see derivative of e raised to power t is e raised to power t and t again, which is 4, cos 5z remain as it is. So, it is 4 e raised to power 3x plus 4y into cos 5z. Now, this implies f y y will be, now differentiate this again partially with respect to y. So, what we will obtain? This is 16 e raised to power 3x plus 4y cos 5z. So, this is second equation. Now, what is f z? F z is, now this is free from z, remain as it is, cos t is minus sin t and t again, which is 5, and this implies f z z will be, now differentiate this again partial respect to z. So, what we will obtain? This is 5 into 5 is 25 minus 25, it is e raised to power 3x plus 4y into cos 5z, because derivative of sine is cos. So, this is third equation. Now, when you add 1, 2 and 3, so what we will obtain? We will obtain f x x plus f y y plus f z z in the left hand side, and the right hand side this is same, and 16 plus 9 is 25 minus 25 is 0. So, this is equal to 0. So, hence we have proved. So, this equation is basically called Laplace equation. This equation we call as Laplace equation. So, we can say that this function e raised to power 3x plus 4y into cos 5z satisfy Laplace equation. Now, what can we say about mixed second order partial derivatives, that is f x y or f y x? Are they always same, or there should be some condition on function f, so that we can say that they are equal at some point? So, let us discuss this example. Example is f x y is equals to x y x square minus y square upon x square plus y square, x y not equal to 0 0 and 0 when x y is equal to 0 0. Okay, let us discuss this example. So, things will be clear after studying this example. So, let us compute f x y at origin and f y x at origin for this particular problem. Okay. So, what is f x y at origin? It is f x y at origin is f x at y at origin, that is del by del y of f x at origin, and that is limit h tending to 0. What it is? It is limit h tending to 0 f x at 0 comma 0 plus h minus f x at 0 comma 0 upon h. So, this is f x y at 0 comma 0. Now, similarly, what is f y x at 0 comma 0? It is f y at x 0 comma 0, which is del by del x of f y at 0 comma 0. That means it is limit h tending to 0 f y at 0 plus h comma 0 minus f y at 0 comma 0 whole divided by h. So, first we will compute f x at 0 comma h, f x at 0 comma 0 and f y at this, then we can compute f x y or f y x 0 comma 0. So, what is f x at first at 0 comma 0? It is limit h tending to 0 f at 0 plus h comma 0 minus f at 0 comma 0 upon h. Okay. So, it is, now you take x as h, y as 0. When you take x as h, y at 0, so this will be simply 0 and f 0 0 is 0. So, 0 minus 0 is 0. So, this value is simply 0. Okay. Now, you compute f x at 0 comma h. We need f x at 0 comma h. Okay. Now, this is, say, now we take limit k tending to 0 because h is already here. So, it is f at 0 comma k h minus f at 0 comma h upon k, okay, at 0 comma h. Now, you replace x by k and y by h. So, what we will obtain? Limit k tending to 0, it is h k into k square minus h square upon k square plus h square minus 0 comma h is when you substitute x as 0, y as h. So, it is 0 whole divided by k. So, this k will cancel with this k, and when you take k tending to 0 here, so it will be minus, when you take k tending to 0, it is minus minus h cube upon h square, which is minus h. So, what we can say about f x y at 0 comma 0? Now, you can substitute it over here. F x at 0 comma h is minus h, you can substitute this value as minus h. F x at 0 comma 0 is 0, so it is 0 upon h. So, this expression will be limit h tending to 0 minus h minus 0 upon h, which is minus 1. So we can say that this value at 0 comma 0 is minus 1. Now similarly we try to compute fyx at 0 comma 0. Now what is fy at 0 comma 0? It is limit h tending to 0 f at 0 comma 0 plus h minus f 0 0 upon h. Now again when you take x as 0, y as h, okay, so it will be 0 and f 0 0 is 0. So this value is 0. Now when you take fy at say 0 comma h comma 0, you see we need fy at h comma 0. So fy at h comma 0 is limit k tending to 0 f at, we need fy, that means we have to change y only, remaining x has remained fixed, 0 comma h comma 0 plus k minus f at h comma 0 divided by k. Now this is limit k tending to 0. Now here you replace x by h and y by k. So it is hk. So it is hk into h square minus k square upon h square plus k square, this minus f at h comma 0, x is h, y is 0. When you take y as 0, so this expression is 0. So it is 0 upon k. So this k will cancel with this k, and when you take k tending to 0, so k will be 0. So it is h cube upon h square, which is h. So what can we say about fyx? So this will be equal to, now here limit h tending to 0, what is fy at h comma 0? It is h. So it is h minus fy at 0 comma 0 is 0. So it is 0 upon h. So this value is 1. So what do we conclude from here? So we have concluded that fyx at some point may not be equal to fxy. It is 1, it is minus 1. For some function fxy may not be equal to fyx. So what is the additional condition required on f, so that we can say that the mixed second order partial derivatives are equal? Okay. So that condition is basically, we have Euler's theorem. It states that if the function fxy and its partial derivatives fx, fy, fxy and fyx are defined throughout an open region containing a point a comma b and all are continuous at a comma b, then only we can say that fxy is equals to fyx. Otherwise they may not be equal. Okay. So this is all about second order partial derivatives. Now we can define higher order partial derivative also, like suppose z equal to fxy, function of x or y. So we can define say fourth order partial derivative also with respect to x, which is f x x x x. We can also define say del cube f upon del x square del y, which is simply del square upon del x square of del f upon del y, or del by del x of del square f upon del x del y. That means del by del x of f, it is yx, or del yx of x. So these are all representation of the same expression basically. Similarly, we may have any higher order derivatives, suppose del cube f upon del y cube, which is f y y y, okay, and so on. So similarly we can compute these values also for any function f, okay. So, thank you very much.